want you to stand up, state your name, tell me where you're coming from and why you're interested in this course. Okay? The reason I want to ask this is so I know like what level of expertise you have on this subject. Okay? So we can start from here, Anton.
Otherwise, my practice ranking was petroleum engineering department. I had gas and environment. And I'm taking this course because I'm teaching a geoscience course to the petroleum engineers. And I would like to know a little bit more about seismic processing and seismic inversion. And hopefully this will give me an opportunity to perform some research in this area.
So, very good morning to everybody. So, I am Nibul. I am coming from IIT Bombay. So, I have taken this course just to explore about inversion methods and to incorporate this in my research. So, that's it.
Good morning, everyone. I'm Prasad Ratu. I'm from IIT Kharagpur. So we work on microseismic monitoring. So my PhD work basically is on signal processing assisted machine learning to improve the machine learning algorithms with the knowledge from the signals. So that is the motivation to take this course.
I'm Manoj from IIT Bombay. This course I have taken because of as part of my PhD. I will be doing the modeling, 3D modeling. So for that I have taken this.
Good morning to all of you. My name is Abhishek Kumar and I'm a research scholar in the Department of Applied Geophysics. I'm taking this course because my PhD thesis topic is related to application of machine learning techniques on geophysical data for environmental hazards studies. So this course will definitely boost my knowledge and will be helpful for me in conducting my research.
Good morning everyone. My name is Kaushal. I am from IIT Mumbai. I'm taking this course as my PhD topic aligning with this course. The topic of my PhD is accelerating large-scale geophysical inversion. So I'm looking forward to get some suitable insight.
Good morning everyone. My name is Kumar. I work in NCM Delhi and I work here as a PR. And I am enrolled in this course because I want to know how seismography can be used using machine learning.
Good morning everyone. My name is Shobhit Chopra. I am a research scholar of ITS and Nanda. I have taken this course because of my work is related to that. I am working in the machine learning application in seismic interpretation. So that's why I am taking this course.
Good morning everybody. I am doing PhD under Professor Department. This course is going to help me with my PhD work because there is of AI. Thank you so much. Good morning everyone. My name is Dr. Ali. I am from IIT Applied Geophysics Department and I am studying this course
Good morning everyone. My name is Arvind. I am research scholar at ITS of Nanda. I have opted this course to boost my knowledge and skill of machine learning and to my research work.
Morning everyone. Myself, I am from IIT. So I am taking this course because my master's thesis is on waveform inversion. So and I am a big fan of radar sensor because I have attended one or two lectures of him at IIT. So I am here for radar sensor to learn from him.
Good morning everyone. Myself is Mohan Verma. I am from Kharagpur. I applied this course and this one is also in L01. So I can learn some basics of our story. Good morning everyone. I am Praveen. I am here for discussing information.
Very good morning to all of you. My name is Dinesh Munda. I am research scholar of IDIS in Bangalore, Department of Applied Physics. My aim to pursue this course is because I am working on predictive mapping using AI ML. So I think this would be very visual learning for me. About this 5 days, 5 days.
Morning, all of you. Myself is Kumar Yadav. I am from Rajesh Arvind School. This topic is boost my research topic. Thank you.
Good morning, everyone. My name is Vivek Vikas. I'm from ITS in Mumbai itself. Currently, this topic will help me improve my fundamentals in inversion theory and machine learning. So, I hope that this course.
Currently, ESNI, my name is Navasula. I am from Patna. I am here to explore
Sir, good morning everyone. I'm Kevin Chatterjee from Wildlife Institute of India, Dehradun. Although I work in the field of wildlife conservation and environmental protection, but I have two degrees in AI, machine learning, geoscience, and geoinformatics, which made me take up this course and I broadened my horizon on this course. Thank you.
If you skip this round.
Good morning. I am Raj Shekhar and I am pursuing my BTech in CSE from Tech University and currently in my 4th year. I am pursuing this course because from a long time exploring the path of AI and ML consecutively with my curriculum, and so it made me more interested in joining this course.
Hello, good morning everyone. I am Nikhil Tripathi. I am a student here at the GAN course, having completed my master's degree in geology from Padu University. My main goal for taking this course is to learn how the AI and advanced inversion methods are transforming geoscience, and I am very excited to gain a hands-on session of this course. Thank you.
My name is Imran Khan. I'm 2014 pass out from geophysics from ITS Hyderabad. Currently, I am a dedicated geophysics and regarding this course, we are extremely happy and we look forward to apply this particular machine learning and inversion theory on our practical data sets and how it's going to resolve better our
Good morning, everyone. Myself, Rajneesh Pandey, superintendent of Inversion from Maryland. As we all know, machine learning is a buzzing word nowadays in the inversion industry. So we came here to gain some comprehensive understanding regarding the machine learning, so which can be utilized in different
Good morning, everyone. I am Kumar Kumar from All India Limited. Currently, I work in I also class out from myself, and I am interested in this course because of its application in specific data analysis. That's benefit our company. We are interested in the specific data analysis for our company. That's why I I am interested in that because it offers a valuable opportunity to learn from advanced concepts.
Good morning to everyone. I am Alvin from L01 Institute of Technology, currently pursuing BTech, and I want to explore the knowledge in machine learning. So I choose this course.
Good morning, everyone.
I come from GSA. I am the first one, and I was told because I get a constraints question. Good morning, everybody. My name is Shekhar. I am currently doing my part-time PhD from this program under the supervision of Dr. Suman Prasad. My research topic is in the application of data science in perfect surface information modeling. That will involve a bit of forward and inverse modeling, and I really look forward to this. Hi everyone, I'm Emmanuel, pursuing PhD at HSA. Appreciated his condition having the research interest in exploration of geosources, particularly focusing on the videos and groundwater. Now, as per this workshop, we add and improve capacity in my side, particularly processing and communication of data. Good morning, everyone. I'm Vinesh Spencer. I'm a third year PhD student from IIT Hyderabad. So basically, I work in characterizing hydrogeology and do experiments and medical studies of fracture networks. So I'm a bit involved in this inversion methods. Currently, I'm working on the machine learning approach on the synthetic fracture networks. So this course, this year course, will help me to better understand or to improve my understanding of the inversion methods. Thanks.
Good morning to everyone. Myself I am currently pursuing second year from Aeronautics Institute of Technology. I came here to take the experience in IIT workshop because my college is type of and how my work
Good morning, everyone. My name is Prabhat Sar. I'm the Chief Geophysicist at All India Limited. I'm attending this course because I want to use it for quantitative income. Actually, I used to do, but I couldn't understand it much. So I believe that this course is going to give a lot of things to me. And in addition to that, I'm attending this course because I want to improve the knowledge of AI and ML, which is quite good to me. Thank you.
I'm Tarun Prashant. I'm a PhD student from IIT Roper. Basically, my PhD topic is in river permeability and distribution. But on the other side, I will be applying the excavating method for subsurface exploration for the shallow subsurface exploration. So for that, we will be using the ERT method, inversion method, to determine the two excavating. So I want to know whether we can improve this inversion, we can optimize the error between for determining the two excavating by using machine learning methods actually, integrating machine learning and the inversion method.
So I guess you all have some idea about what this course is about. So we will first, at least half of the course will be focused on inverse theory, and the other half would be on machine learning. And the reason I decided to have a course discussing both of these is because there are a lot of elements in inverse theory that are common to machine learning. So I really want you to pay attention to all the discussions on inverse problems, how we solve those, and how we formulate those. because that will come in that will be very important in your understanding of machine learning. So some of the resources, you will get all these slides, okay? And maybe I'll just have those copied right after my talk. But from tomorrow, we'll try to give you the slides ahead of time, okay, so that you can scribble on those if you like. So these are some of the important books on inverse theory. There are 3 books, and then there are 2 more books you can look at. And then we have some other resources. A lot of these machine learning and inverse problems, they require manipulation of matrices. Sometimes large matrices, sometimes sparse matrices. So how do you compute those efficiently? And one common thing that you will recognize is that both inverse problems and machine learning make use of optimization. Okay. Now this book is actually very good. It's a very simple book on optimization, and I think you can download this PDF version somewhere for free. So I would strongly recommend you guys to look at this book in case you haven't seen it, okay? Okay, so what we expect you to do is first understand what is an inverse problem, okay? And then what to expect from data. So what we're going to talk about in the entire 5 days of 2 classes is how to make some inferences out of data. Okay, so we go, like somebody said, they are trying to calculate some shallow shear velocities for building construction purposes, civil engineering purposes. So how do we determine those? For that, we send in some surface waves, and then looking at the velocities, we try to quantify what the salt structure and what the soil structure looks like, right? And then there is other type of problem where you all watch Netflix, right? So whenever you turn on your Netflix as your username, then it comes up with some suggestions as to what kind of movies you might want to watch. And that is because Netflix is generating some data to identify your behavior, what kind of movies you like to watch, and based on that, they make recommendations. So in both cases, we have some data, and then from the data, we want to make some inferences, right? So that's what basically we will be doing, and that can be done either by using physics-based methods that are called inverse methods, typically, and then some completely data-driven method, which is typically a machine learning method, okay? So everybody in this room is basically from science background, so you're all familiar with calculus, linear algebra, and statistics. And optimization is something that you may not have seen, but I will focus on that. And then some degree of programming. So we will give you some assignments, and what I would like you all to do is to do those in groups, because I know some people are good with programming, some people are good in math, and some other people have good practical experience. So you can make groups and then do those as groups, okay? So that way you will learn much quicker. Okay, so first thing is, what is inversion? Now I started to work on inversion more than 30 years ago. And those days, people didn't know what inversion was, and they didn't even like it. And the common perception was that if you tell somebody you're doing inversion, and the people will say, what I'm doing is inversion, and I don't know what you're doing. So every time you go and talk to somebody that you're doing inversion, says, what is that? I'm already doing inversion. So, and then this was actually very common, like what they're doing is inversion, so it can't be of practical value. Okay, and that was something that we learned, that we heard in our industry for a long time. And it's quite amazing that after 30 years, almost every company is using some kind of inversion, okay? So, and the reason that this kind of perception grew in the community was that the original work of inverse theory was actually developed by some people who were really high-powered physicists and mathematicians. And some of the papers they wrote were difficult to understand for geoscience people and some other people from other specializations. And those who actually did understand those, they kind of thought they were some sort of geniuses, and they used to go around with their noses high up in the air, and that is the kind of impression people had. But now it has actually become quite important. So if you look at how we actually learn from observations, the bottom line is how we learn from observations, right? So I came across a very nice quote from none other than Richard Feynman, who was a Nobel laureate physicist, and he says that in general we look for a new law. For example, how the Newton's laws of motion or Hooke's law, they were formulated, right? So the first we guess it. So you apply some force and then you see how much displacement takes place, right? And then you start to think that, okay, if I increase the force, I'm getting more and more displacement. So that becomes a law, right? So first we guess it, and then if this law is correct, then any future observation you can make, you can predict it, right? Then you can say that once I have a law that force is proportional to displacement, then you can say, okay, if I apply certain amount of force, this is the kind of displacement that we can get based on the type of material, right? So that is how Hooke's law was formulated, for example. So now, let's say that you come up with a hypothesis, some kind of law, that the force is inversely proportional to displacement, or force is square of displacement, or something like that. But then based on that, if you make a prediction and that prediction does not match, so then what do? You change the law and then repeat this procedure until you have something that follows, that makes predictions of the observations. So there are 3 steps here, basically: guess, compute, and compare. You guess certain relationship between your observation and your prediction, and then you make do a computation, and then you compare. If that does not match, then you change your model and go through there. So this is pretty common learning process. It doesn't matter what kind of learning you are involved with. As human beings, this is how we learn, right? We touch some red hot thing, and then if it really hurts you, then you know that this is probably hot and we should not be touching it. Otherwise, you may think that this is just red color rod, right? So this is how the entire learning process involves. And what we are doing here in inverse theory or machine learning is trying to put in some equations in there, okay? Okay, so what is inversion? Let's say that I have a set of physical variables, okay? And that depends on what kind of problem you are interested in. I understand that here we have people from different disciplines, but in geophysics, for example, we have parameters such as porosity, permeability in a reservoir, or P wave velocity, shear wave velocity, and density. Now, given these parameters, if I can predict my data, that is called a forward problem. So remember that law of physics that I told you about? So here, what I'm saying is that I have a set of parameters that describes this. So let's take, for example, Hooke's law, right? So force is proportional to displacement, and then there is a constant term here, right? And this is the elastic coefficient, right? So what you do is that, so this is my formula, right? So here my observations could be force and displacement, but I'm trying to estimate K. So given a K, if I can compute the displacement for a given force or compute F for a given displacement, this is my forward problem. Forward problem means give me the parameters, for example, K, and predict the data. So typically, this involves some kind of equation, typically a partial differential equation or some form of equation, okay? Now, our problem is just the opposite of that. We have some observations, and from there, we want to know what the properties are, right? So we want to be able to predict these variables from these measurements. And for example, on Earth, in Earth sciences, we're trying to understand what's happening inside the Earth. We're not able to see anything. So we are making observations on the surface. So from the surface measurements, how do I back out rock properties? Okay? So that's an inverse problem when you go from measurements to physical variables. Okay? Now I call this a naive definition. Okay? Why do I say that? So the reason I say that is that going from physical variable to measurements, you have a deterministic equation. But when you go from measurements to the physical variable, you have to have perfect data that follows your physics equation, right? However, your data are never perfect. So it's not always possible, almost it's never possible to get exact model from the measurements. But you can get some kind of an estimate, okay? So what we normally do is we solve it using an iterative forward modeling. So here we assume a model of the unknowns. These are our unknowns. So I assume that some values of the unknowns. So if I give it some value of the unknowns, then I can generate my theoretical data by solving that equation, right? Then I can compare it with my observed data, and if they look the same, then I say that I found my answer, and I stop. Otherwise, I have to update my model, redo the forward calculation, and repeat it. And this is done using optimization. So there are multiple questions here. Number one is how do you measure the similarity, right, between the two data? Is there any unique way of defining that? We'll look into that. Then number two is how do you compute your updates, right? And we will look into those, okay? The first thing that you do in solving an inverse problem is to identify what's your data, what are your unknowns, what is your forward modeling equation, okay? And then you try to answer these questions. Okay, so first of all, that definition I gave you, from data to model is your forward problem, model to data is your forward problem, and then data to model is the reverse process. Like I said, this kind of definition of inversion is wrong because we don't have perfect data, okay? And because of that, our problem is what is called ill-posed, so you can have multiple solutions. And the data can be noisy also, okay? So a better definition or a practical definition of inversion is interpretation of inaccurate, insufficient, and inconsistent data, okay? So what this means is that from a model, I can go to the data using my forward operator, but from the data, I can't really get my model exactly, but I will get an estimated model, and maybe we can estimate uncertainty in our answer. Like how much confidence we have in our answer. Okay? Okay. So what I'm going to do in the next hour or so is basically review some basic notations, define something called norm, and talk about linear and nonlinear problems, and a few other things related to inversion. Okay? Okay, so this is the kind of notation that I'm going to be using. This is my observation, which I call data vector, and this is my model vector, that's our unknown. Okay, so this we have discrete data, so this is all digital data. So you can think of this as a concatenated set of numbers in a vector, and these are the unknowns. Okay, nd is the number of data points, nm is the number of unknown parameters, and that's our forward modeling equation. And in general, this is a nonlinear equation. Okay, and remember that we almost never have the number of data points equaling the number of parameters. Okay? Okay. So, in an inverse problem, what we want to do is to determine some model that can minimize the misfit between observed and synthetic data, right? Remember that picture I gave you? You generate some theoretical data and try to see how well you are predicting it, and you try to minimize the difference between those. So here is the difference between observed data and synthetic data. Okay? And I write this as boldface. This is my vector, right? This is a vector, this is a vector. So E is also a vector. So one of the ways you can calculate the difference between observed and synthetic data is simply take the absolute value of the difference, square it, and then sum it, and then square. Okay? This is your minimum square error, right? So when this becomes small 0, then you say that this is my best model, right? So in vector notation, you can write it like this. But it turns out that this is not the only way to measure the difference. You can measure the difference using what is known as LP. This is called an L2 norm or Euclidean norm. Okay? And this is an LP norm. So what we do here, we take the absolute value of the error from each sample, sum those, raise it to the power p, and take a pth root. So if p is equal to 2, that's your standard square error that we are familiar with, right? Now, if p equals 1, then we call it L01 norm. And when p becomes very large, then we have this. So probably I got you guys confused, right? Because always we think about making the difference, taking the difference and then squaring and summing, right? So why am I telling you about p norm with other options, right? So to do that, we will look at this particular picture. Okay? Now everybody has, in this room I think everybody has worked with like fitting a straight line, right, to some data points. So let's say that this is my x and this is my y, and these are my open circles are my data points. And you are fitting a straight line. Now I gave you choices as to what kind of norm you can use. When you use different orders of norm like L1, L2, and this is actually L15, remember this is noisy data. Okay? Now, all that I am saying is that when you run different straight line fitting, you have different answers depending on the type of norm that you use. So what is the difference do you notice here? Anybody? With the change in the norm, what do you see here in terms of fitting? Error is increasing. What else are you seeing? So what you see here is that higher the order of norm, more it is influenced by large error in the data, right? That is one thing just we noticed that yes, it does make a difference, right? But this does not tell me then which one we should use, right? Which one we should use? Anybody guess? How do you know that that is less error? Okay. So when you say large error for L15, you are absolutely right that L15 measure gives you large error. Okay. But that does not mean it's a bad one. If all data points were, if the data were not noisy, that means you are assuming that this is a part of noise, right? So the type of norm that you use depends on noise in the data. Okay? Unfortunately, we don't always know what is the type of noise we have in the data. So we use L2 norm. And L2 norm is a good compromise. Okay? Yes? Physical significance?
Like when we say then you are basically trying to say that how far your data is, or maybe in terms of statistics, how the data is.
How well your model is predicting your data, okay? But then how well is your model predicting your data depends on noise in the data, okay? So if the data, you assume that it's a perfect data, then I would use L1 norm, okay? This is a robust norm. So it basically is least sensitive to outliers. So typically we do use L2 norm because that's a kind of a compromise, okay? So L2 or L1 norm generally is what we use. But we will show you a clever way of using L1 and L2 norm both in linear regression and in machine learning, okay? Okay, so again the answer is related to the statistical distribution of error in the data, okay? But I have already explained this to you. Okay, so classification of inverse problems. So I remember I said that my forward problem is D equals GM, right? Where G is the forward modeling operator. Now for some problems, this G, this can be written as a matrix G. The main point here is that this G is not a function of M, okay? So if I talk about the straight line fitting, Y equals, say, A naught plus or A plus BX, right? Now A and B, these are not functions of X. So this is a linear problem. You could also have Y equal to X squared plus BX plus C. This is a quadratic equation, but it's quadratic in X, not in your parameters A, B, and C. So this is also a linear equation. So if you can write this as a matrix times a vector, can we just say that my model is G inverse D? Who thinks we can do that? Raise your hand if you think we can just simply invert the matrix. Anybody else? Don't feel shy. I really am asking you to. You have to vote one way or another. How many? Yes, we have in the class. Okay, 2, 3, 4, 5, 6. And how many no? And rest? No vote, huh? Okay, so there is a reason we cannot really invert our G matrix. What is the condition for inverting our G matrix? First of all, the G matrix has to be X square matrix, right? But your number of data point and number of model parameters are not the same, so it's a rectangular matrix, so we cannot do that. Now, even if your G matrix was a square matrix, there's no guarantee that it's invertible, right? Because that may be rank deficient. So we try to come up with some approximation value of G, and we call that generalized inverse. Okay, so given this D equals GM, we have different scenarios: underdetermined, overdetermined, and mixed determined problem. And this is something Somen will go into more details of. So I will skip those, and I will straightway go to this particular case. There are a couple of things you should know whenever you're talking about inverse theory, especially these came from the concepts of linear inverse theory: existence, stability, uniqueness, and robustness. So what is the existence? The existence implies that the solution G inverse exists. We already discussed that. Uniqueness means that if you have two solutions, M1 and M2, that gives you data, D1 and D2, then D1 should not be equal to D2. If two different models give you the same data, the solution is non-unique, okay? And stability is how small errors in the data propagate into the model. And robustness indicates the level of insensitivity with respect to small number of large errors, and I'll show you in a second. So typically, our problems do not possess uniqueness and stability, and for that, therefore, we have to use some tricks, okay? Okay, so here is an example. So you see that this equation, x plus y equals 2, and x plus 1.001, y equals 2.001, and you can solve it, right? It's two linear equations, two unknowns, and your x equals y equals 1. Okay? Now, let's say that you have some error in your instrument, okay? Some measurement error. And what you have is that it's not sensitive to fourth place of decimal. So what we have is x plus y equals 2, x plus 1.001 y equals 2. So now what is the solution? The solution changed significantly, okay? So small error in your observation is causing large error in the solution, and this is very, very important. You have to remember, I just gave a small example to be able to appreciate this, okay? So similarly, there's another example of non-uniqueness. Okay, so given a linear inverse problem, we have, this is our error function. So what we do is we take the derivative with respect to the model parameter and set it equal to 0, and that gives us a solution for the model, okay? Remember, from M equals G inverse D to we have M estimated is equal to G transpose G inverse G transpose D. So now this formula is different from just inverting the G matrix, right? So can we use this for finding the model? You still need to invert a matrix, right? Which is this matrix, GTG. So can we invert that matrix? How many of you think you can? Raise your hand. Why do you think you can invert this? This is a symmetric matrix now, right? And this is a square matrix. Not necessarily symmetric, it's a square matrix, okay? So you expect that you can, except for the fact that this may still not be invertible because this may be rank deficient, okay? But this is better than what we had to start with, okay? So here we have D equals GM, which is our forward problem, and this is our solution. And this is what is always used in what is known as linear regression. Okay? Because G is a linear operator, and you hear people talking about linear regression, and this is really what you are doing there with some modifications. And why do you need to make modifications? The reason we want to make some modifications to this is that this GTG may not be invertible, right? So then when we have the fully nonlinear forward model, an objective function is nonlinear, then that least squares method that I showed you earlier, GTG inverse, is not going to work, okay? You have to use some other method. We'll talk about that. So let's look at some examples of inverse problems. You can have gravity and magnetics. You measure the gravity field and magnetic field, and from there you want to measure like density and magnetic susceptibility in the subsurface. Seismic tomography and earthquake location. We have deconvolution problem, we have Fourier transform, AVO. In reservoir engineering, we have history matching. In medical imaging, we have CT scan and ultrasound and so on. These are all some kind of inverse problems. Okay? So let's look at the fitting of a straight line, okay? Let's say that, any trouble hearing me? What about people at the back? Can you hear me all right? Okay, so here is an example. Let's say that you go to Jharia coal field, okay? And you drill a borehole. And what you do here is at different depth, you want to measure temperature, okay? Just simple with a thermometer. And one of the things that people mostly talk about for many applications is thermal gradient, right? How the temperature is increasing or decreasing. So what we do here is we fit a linear model. Temperature is equal to A plus B times Z, which is the depth, and B is the gradient and A is the intercept. So now for different depths I have different temperatures, and I can use this equation A plus B Z1, Z2 all the way Zn. Now I can write this in the matrix form, and here I have the temperature, I have the depth, and I have A and B. So now I have this linear problem, D equal to Gm, so I can do a linear regression and I can get the solution, okay? Similarly, I could be interested in fitting a parabola, right? So I have A, B, and C, and then I have an equation looking like this. We still have the same D equals Gm, but this is still a linear equation because it's nonlinear in Z, but not in parameters. Okay? It's very important to recognize this. Okay, so this is one example that we talk about a lot in geophysics, where we want to invert gravity anomaly. And we will give you a homework, we will give you a class exercise to do this. So this is a natural source experiment where what is done is some observer will walk on the surface with a gravimeter and simply measure acceleration due to gravity. And from there we want to come up with the density distribution in the subsurface. So here what we would like to know is the density and shape of the body. So what we are interested in some kind of anomaly in density, okay? And those bodies can give us some useful information depending on the objective. So we want to know what is the density contrast here compared to the background and what is the shape of the body. So here we identify the forward problem, and the forward problem is rho times g r cubed dx dy dz, okay? So what you see here is this r is what defines the shape of the body, and rho is the density of the body, okay? So is this a linear problem or a non-linear problem? That is my question. I have not put it in the matrix form, but I'm asking you. Is it a linear problem or a non-linear problem? Speak up if anybody. You've all seen gravity and gravity equation, right? Okay, so here in general is a non-linear problem because you have this common denominator, right? So if you are interested in just finding the shape of the body, keeping the density constant, that's a non-linear problem. But if you fix the shape of the body, only interested in computing the gradient, then it's a linear problem. So it all depends on how you pose your problem. This can be a linear or a non-linear problem, okay? So approach 1 is the shape of the body is known, and estimate density. So that's your linear problem. And approach 2 is somehow you know the density, you want to find out the shape of the body, and that's a non-linear problem, okay? Okay, the second thing I wanted to show you is seismic tomography. So typically, we have earthquakes that are recorded on instruments called seismometers around the world. And from the arrival recordings of PNS waves, we try to locate the earthquake and also try to find out the velocities, right? Now this is basically a ray path from source to receiver. Now we have data as the travel time of the particular wave at a given receiver from a given source. This is your velocity and this is your location, and the travel time is very simple. You simply take the distance divided by velocity. So if this is your ray path, if I break it up into small segments, and in each segment if I assume that the velocity is constant, then it should be just distance divided by velocity, right? Or slowness times this, when slowness is nothing but 1 over velocity, okay? All right. So we have to basically be able to solve for, say, the slowness distribution or velocity distribution. Now the problem here is that we can write this again in this matrix form, where this L is your length of the ray and this S is the reciprocal of velocity, and you can put it in this grid, right? So here you have a source, this is your ray path, let's say this is your receiver, and these are different blocks of slownesses. And that's your travel time. So you can write this in this notation. These are my ray path length, this is my slowness, and this is my velocity. So I have this equation. So this looks very much like what we saw earlier. So is this a linear or a nonlinear problem? Any seismologists here? Anybody who's doing seismic work with earthquake data? You probably don't want to say that now because I'm going to ask you a question. Now it looks like this is a linear problem, right? But remember what I told you earlier. In a linear equation, this G should not be a function of M. But these are ray paths, right? But if you change the velocity, then your ray path is changing. So it's actually a nonlinear problem. Sometimes people solve this as a linear problem, but by saying that my model, my velocity is not changing much, so I will not change the ray path. But in general, this is a nonlinear problem, okay? So this is the one, and okay, so next one is X-ray imaging. So the reason I want to show this is that you'll be amazed as to how well this relates to the seismic tomography that I talked about. So what is done in X-ray imaging? You send an X-ray, and then you actually measure the strength of the returned X-ray, right? You know the incidence X-ray intensity, and you also know what is received here. And the physics or the basic equation that relates this is ds is minus c, where the c is the absorption coefficients, okay? And that is basically the property of the material which we are interested in. So the way this is solved is they linearize it. How do they linearize it? They use this equation, approximation for the exponential, and then they get an equation that looks like this, which is a linear equation. And all that they are doing is a linear regression. Okay? So let me show you a couple of examples here. We'll go to this one later. Okay, so here is your X-ray example. You have all of these, or it could be your standard tomography also. So you have a whole bunch of these transducers, and the rays are transmitted through a material, and then you're measuring it all in a circular pattern. Okay, and all that you're interested in is imaging this. Imaging this basically means finding that coefficient. It could be velocity, or it could be your X-ray opacity, X-ray coefficient, right? Similarly, you have this. So with this positron emission tomography, we can get images like this using a ring camera. Okay, and you can also, actually insert some of these receivers within the body. Here is an example. There's a multi-electrode mapping west for obtaining body surface potential maps. This sounds very much like geophysics, right? Just that it has been applied to human body. The basic theory is the same. Okay. Here we have seen this kind of pictures a lot, right? And all that they're doing here is using acoustic waves. Okay? And this is an image solving an inverse problem here. So this is ultrasound imaging. This basically is called sonography. And here you can see a patient is on the table and the nurse is putting the transducers. And in real time, it's able to get to this. Okay? So this is something that we would also like to do. The oil company people, they go to the field and collect a whole bunch of seismic data. Then they come home, and how long does it take before you get an image, sir? How long does it take from the field measurements to getting a migrated depth section? You go to the field, you collect 3D seismic data, and then after you have completed your survey to when you get the image, how much time is spent?
Let's assume we have got 100 square kilometers of the area. Then it depends which part of the country we are surveying. In Assam, it is so time delay is very less. So say for 3 to 4 months. So 3 to 4 months, right? 3 to 4 months. So typically we will not see that. We will acquire the data. Then you will process the data. So it will take only 6 months. Yeah. So our knowledge is so much higher.
But the theory is the same. Here they're doing it in real time. We're using all possible high-powered computers. Still, 6 months, 1 year, depends on what you're trying to do, right? You have to be able to, you should be aware of that. The basic physics and other things are very, very similar. Just that we have so many unknowns. And because of that, it takes a long time, okay? And large volume of data. So this is an inversion from gravity data. And so from where we could compute some, this is a very interesting data set. We had some data set in Antarctica. So there was a lake, and the lake is frozen, so we didn't know the depth to the lake, bottom of the lake. So then gravity data were collected. These are airborne gravity data. So helicopter was flown over the lake, and we got the data. And then we actually inverted those, and this is the bottom of the lake. Okay. Huh?
By using the gravity, the lake bathymetry is done. Lake bathymetry.
Yeah. But the lake is frozen. So we don't know this. So that's why, and we didn't do any seismic survey. So gravity data was used for that. Yeah, exactly. Yeah. Okay. There were a couple of seismic lines we used as constraints.
What is the principle behind that? Lake that how it is given?
Oh, it's a simple gravity formula that I showed you. So all that we did was solving for the lake bottom, but we assume that we know the density of because we know the density contrast here, right? Basically compared to the background, ice density is typically known. So we fixed that and then we calculated this. Okay? So this is a very important application. And this has far-reaching implications because they also want to know when the ice melts, how the glacier is going to propagate and things like that. Okay? We also use seismic travel time data to calculate the velocity structure.
Determine the glacier deposit volume.
Yeah, sure. Yeah. And then these are some of the other applications. This is one application of a submarine volcano and some of the faults that we have imaged using solving and inverse problems. Okay. And this is something that oil industry people would be interested in. So this is one area where we're trying to invert for density, and so essentially use those to demarcate the pay zones. Okay. Then we have MRI images. This is your pre-chemotherapy, post-chemotherapy, 2 months and 4 months. So this is using PET, positron emission tomography. And see, even I cannot tell anything about whether the cancer has been cured. These are the images of a cancer patient. The only thing we can say is that the images are different, right? But what kind of images are these? These are your time-lapse images, right? But we can go to an oil field and we can look at the time-lapse images, right? And that we can interpret and we can tell which way oil has swept, right? So again, the principles are very similar, but our part, which is the interpretation of these images, is not trivial. Okay, there's a lot of unknowns. So in everyday life, we're always solving some inverse problems. So it's very important to learn how that works. And that is what we will actually do. Okay, so that's all I had. And is your talk next, or should we take a quick 5-minute break or something?